Okay. So, okay, let me start with this new chapter, which is about optical oscillator and resonators. Um, why I'm talking about this? Because the laser is an optical oscillator, uh, and in order to understand the laser, first we have to understand what the optical oscillator, or in general, what an oscillator is. Uh, you can think that the optical oscillator as a black box, okay? And this black box is whatever it takes as an input, it produces a signal of oscillating frequency, or it is producing a signal of some kind of uh, you know periodic, aperiodic, or etc. Okay, and in here, what you see in the picture that in fact this black box is going to be replaced by our laser, and we call a laser as an optical oscillator, or in general an oscillator. And what is an output for a laser? It's the laser light itself, right? But we know that laser light is an electromagnetic signal. Okay, light is an electromagnetic wave, and since we are describing the light as a wave, it means that it is an oscillating property. So that makes laser an oscillator. Okay. Well, these oscillations, the signal oscillation, I mean, in general, oscillators are producing not only light oscillations or electromagnetic oscillations, but they also produces mechanical oscillations, or they also produce pure electrical oscillations, etc. Okay, it's not unique to laser or electromagnetic waves. Any kind of signal that is changing the amplitude in this fashion, okay, is described as oscillator. So what you see in this oscillator, a spatial oscillator, it produces a pure sinusoidal signal. Okay, what I mean by a pure sinusoidal signal is that when you look at this picture, the signal is a perfect wave with a fixed amplitude. Okay, and it is, coming and going infinitely. This, in fact, you only see very short, limited piece of this signal, and the signal is, going in this direction infinitely, and in this direction also infinitely in the time axis. So this is an ideal sinusoidal signal that we already have discussed in our previous lectures. And you see the signal in time domain, okay? And sometimes, of course, this signal is going to be limited over time. In that case, this length of the signal in time is going to be described as tau, and tau is going to be lifetime of your signal, okay? But for the time being, if the tau is infinite, what you get in the frequency domain is that this signal frequency, which we describe as f0, okay? And somehow, if again, as I said, this tau is limited, not infinite, if this tau is limited, you will see that in the frequency domain, this sharp line is going to be a kind of bell shape, okay? It's going to be a bell shape line. Like, what I mean is that you're going to have this kind of distribution, okay? A bell shape distribution. If you have tau is limited, if you have tau is unlimited or infinite, what you get in the frequency domain is only a sharp line, okay? So I think we might have discussed that this delta F, or the bandwidth, sometimes we call the bandwidth of the frequency domain, is just equal to inverse of this tau. Okay, whatever you see the tau, the length of the signal in the time domain, if you take the inverse of it, okay, you will get the width of this distribution in the frequency domain. So what I'm trying to describe you is that, the output of a black box oscillator. Okay, this is one option. All right. So next thing is, okay, next question, how can we produce or how to make an oscillator? All right. Well, as I said, there are many different kinds of varieties in oscillators. One very simple example is that this pendulum, right? You just have a string which is fixed to an attached point over here, it might be a ceiling or some fixed point. And the other end of the string is attached to kind of mass, okay, a solid mass. And if you just, deflect the string with the mass from the vertical line and release it, this will swing back and forth, right? It's usual simple pendulum. So this swinging back and forth is nothing but a mechanical oscillator. Why? If you think about the amplitude to be the distance of this mass, okay, distance of the mass from the vertical line over time, if you draw uh, this amplitude, if you take this axis to be z anyway, okay, and picture about this z amplitude with respect to time over time, you will see a kind of oscillation, right? Like this, when the pendulum is swinging back and forth. And you might ask these questions that, okay, if you have some parameters like the mass of the, object, which is tied to the string, the length of the string, let's say is d, and what else? We have also the gravity, right? Because if you are doing this oscillations on the surface of Earth, we have G, the gravitational pull by Earth. If you do these oscillations in, let's say, on the surface of Moon, you will see the oscillations will be, slower. Okay, so you might think that the gravitation or the planet that you are making this oscillator makes a difference if you are building a simple pendulum anyway. So if you look at just textbooks, or if you can also derive by yourself that the frequency of these oscillations is nothing but this is f0, the frequency of these going back and forth things. But what we define as frequency is the number of swinging back and forth in 1 second. Okay. So if you calculate this, is going to be like 1/2 pi in square root g, the gravitational constant g, which is 9.8, divided by d, the length of the uh, string. So this is going to be your frequency. Okay. And when you look at the amplitudes, you will see this signal. Well, if you are careful about looking at this signal over here, the amplitude is decaying. Why is decaying? Because if you just release this mass once and let it go over time, you will see that these oscillations will die out. Okay, they will be eventually die out in the amplitude, and it will stop eventually. So it's kind of decaying amplitude. All right. Because of this decay in the time domain, okay, if you it, it will be, what it will, what it would be if there is no any decaying, if the amplitude will be constant over time infinitely. You knew what it would be look like in the frequency domain. It will look like just a sharp line. If there were no any amplitude decay, okay, then in the frequency domain you will observe that it's going to be a sharp line. But since we have a decay on the amplitude, okay, this is called damping. In mechanical oscillators. Also, damping is very general. It's there for all kinds of oscillations, all kinds of oscillators. We also have damping in the laser. Okay, and damping means simply the amplitude of the oscillations will decrease over time. This is called damping. If you have damping, this damping will show up in the frequency domain as largening the width of the distribution. Okay, you have a larger damping. That means in a shorter period of time, if you have these oscillations going back to zero, then you will observe a larger width on the frequency domain. If you have a very small damping, okay, then you will see that this width is going to be narrower, slower, or sorry, the less decay or less uh, damping, uh, narrower bandwidth. Okay, larger damping will produce larger damping. All right, but you know what this means in terms of the tau. The tau is the lifetime is a lifetime parameter for dampings of large. That means if you have a large damping, then your oscillations will go back to zero quicker. That means tau is smaller. Larger damping means smaller tau. Smaller damping means larger tau. Okay, just in order to you compare these. So whenever there is kind of loss, this is called loss. Damping is a loss, kind of loss. Okay, whenever there is a loss, there is this kind of this width of the distribution in the frequency domain. Okay. Well, this is what I was trying to tell you in the previous slide. You see, in this picture, the damping is large. When the damping is large, it produces a larger width in the frequency domain. When the damping is small, it produces a narrower bandwidth in the frequency domain. Okay, but larger damping means, let me also write over here, larger damping, this is larger damping. Okay, larger damping means tau is small. Okay, uh, as you increase the damping large, tau is getting smaller and smaller. If you have smaller damping, less damping means tau is large. If you have zero damping, that means tau is infinite. Okay, so all right, and this is what it does. Well, so it seems that having this damping, right, is kind of making a bad oscillator. All right, if you have damping, that means you have a bad oscillator. If there are losses, but how can you overcome this loss? Can you overcome this damping, or can you decrease this damping in some way? Well, mechanically you can. If you drive, if you drive, if you drive these oscillations, or this swing or the pendulum with an external force, but this force must be periodic. All right, then there's a chance of decreasing this damping, so that you might have a zero damping oscillator. Okay, so you can principally you can get rid of the damping by using an external agent. Okay, external driving force. We call this external agent as the driving force in the case of oscillators. If you have a driving force, this is called driving force. This is driving force. Okay, driving force. Of course, this driving force must be periodic. It's a periodic. Whenever you say that something is periodic, it has some application frequency, right? While this pendulum is having its own frequency, okay, let's call this f0, right? F0 means, number of swinging back and forth in 1 second, in 1 second. And in the other hand, if you have a force of a, sinusoidal in nature, this will have its own application frequency, right? Because if you apply a force which is periodic, it must have some frequency. Whenever there is period, there is always a frequency. The question is, uh, what is going to be your force frequency, okay, so that this driving will get rid of the damping in your oscillator, okay? It appears that if you call this force frequency as F, it appears that this force frequency, external force or driving force, which is closer to uh, frequency of the frequency of the oscillator, then you might have the chance that to get rid of this damping. Or otherwise, if this F is very different than F0, if it is very large or if it's very small in compared to F0, the driving force, you will not get rid of this damping, even if this force amplitude or the amount of the force, even if you are driving is stronger and stronger, since your frequency is not matching up with the frequency of the oscillator, you might end up not getting rid of this damping. Okay, you might worsening the things. You get worst or the worst case in your amplitudes of the oscillation. Okay, and and this is the case where we call it resonance, right? I don't know if it is resonance. If there is some oscillating system with some natural frequency, okay, or eigen frequency, this frequency of the system, the oscillator, is called natural frequency of the system, natural frequency, or sometimes it is called the normal mode, or sometimes it's called the eigen frequency. There are many different names that describes the same thing. You might see it in some various textbooks. Okay, this is the natural frequency. This is the eigen frequency, or the normal frequency of the system. If you drive your system frequency, a, a driving force of frequency which is close to its natural frequency, then you get the case of resonance. Okay, and I will describe what this resonance is more and more. Okay, do you have any questions so far? So far, I'm trying to explain everything in its very basic format. Okay, in this slide, what you see is there are many different kinds of oscillators. Okay, and there is this simple pendulum, and there is the spring mass system. Okay, you can also get some oscillations if you attach a string to a fixed point and the other end attached to a moving mass, and if you provide a very less friction surface or almost zero friction surface, if you are able to, then if you just pull the mass and release it, the mass will go back and forth, okay, like this. and this is a spring mass system, and it will have its own frequency, and its frequency is given by 1 over 2 pi in square root k divided by m, where k is the spring constant. It's a parameter that describes your spring. If your spring is hard, if it is hard, it is harder to pull or push, then you have a larger k. But if you have a soft spring, then k is small. Okay, k describes the hardness of the spring, and naturally, if you have a harder spring, it's going to be moving faster and faster. It will increase its frequency, and as you expect, the frequency will be proportional to the k or square root of k. Okay, but if you have a larger mass, it's going to be harder to move the mass, uh, harder to move the mass quickly. That means it will have a negative effect on the frequency of the system. So the frequency is depending inversely to the mass of this mass of the system. Okay, mass of the system is just the mass which is attached to the spring, and in this case we just ignore the mass of the spring. Okay, you can ignore the mass of the spring if you use a very large mass in compared to the spring mass. So there is no effect of mass of the spring over here. But of course, in fact, in reality, there is a little effect of this mass of the spring in the frequency, but it is not shown in here. It is the basic form. So the third oscillator is, as you see, is nothing but a taut string which is pulled between two fixed points, just like a guitar string. Okay, it's like a guitar string. When you pull as a guitar string and release it, what you, you get is just oscillations of the string and producing a kind of note sound. And if you have this length between these two fixed points, and if you know you have a speed of the wave on this taut string, the frequency can be expressed in terms of these two parameters. The speed of the wave in the spring, Vs, divided by twice the length of the string, will give you the frequency of this amplitude of oscillating up and down of the string. Okay, and the last example is just an LC circuit. It's an electrical circuit, and this kind of electrical circuit is supposing that the cable is the cable connecting the capacitor and the inductor has very small resistance. If you ignore the resistance of this cable, and if you start this circuit with a fully charged capacitor, this capacitor will initiate a current initially flowing, let's say, in this direction, in the counterclockwise direction. But as the charge in the circuit is getting transferred to the other plate, the circuit will produce the opposite current. You start with the current in this direction, okay, but later, for some time later, when you observe the current will just reverse, okay, in this direction. So this changing of the direction of the current on this circuit is happening periodically, or it is happening with the number of times per second, so that it has some frequency. And this frequency of the change of direction of the current in this circuit, LC circuit, is given by this formula. Okay, it is again 1 over 2 pi in square root 1 divided by the magnitude of the inductor, L, and multiplied by the capacitance of this capacitor. So you see these oscillations you can produce or signal in every kind of system. All right. Uh, you know, as you have naturally damping in all kinds of these oscillators, you will observe this kind of behavior, okay, in the time domain and the frequency domain. And as I said, it is always possible to express the width of the uh, distribution in the frequency domain in terms of damping parameter of the system. But if you have a good oscillator, that means this bell shape is narrower. If you have a bad oscillator, this bell shape is wider. Okay, and our aim is going to be to find the ways or methods how to decrease the width of this uh, distribution in the frequency domain for a specific kind of oscillator. Alright. Evet. Hayattasınız değil mi arkadaşlar?
Evet hocam.
Okay. So let's move on. So if we sum up, if we make a summary, then to make a oscillator, first we have to have a resonator. I mean, an oscillating system together with a driving force, and we require a low loss. We want a small damping, and in order to overcome this loss, we need to have a driving mechanism. Okay. You will observe that this driving mechanism is going to change. For mechanical oscillators, it is just a driving force, a mechanical force. But for electrical systems, this driving force is going to be replaced by a AC power supply. Okay, AC power supply will produce changing, voltage difference between the terminals, between the two terminals. Okay, and if you connect this to a circuit, if your circuit is an oscillating circuit, this circuit will be, derived. It will be derived by this power supply, AC power supply. If your oscillator is a mechanical oscillator, okay, just this kind of force you apply is going to be your driving force. Well, if your oscillator is a laser, what is going to be your driving force? We will come to this point. So, as I said, the laser is a resonator, and in fact, it's an oscillator with a driving mechanism. This is what makes a resonator. If you see as a resonator, then that means it's an oscillator with the driving mechanism. Okay. If you don't have a driving mechanism, you don't have a resonator. You have only an oscillator. Okay. But if you have a driving mechanism, then together with this oscillator, you have a resonator. All right. So this simple picture over here describes your laser. Okay. What is it? What do you see over here? You see over here two mirrors with these letters described as M. These M's are mirrors, and the reflecting surfaces are facing each other. Okay, these inner faces are reflecting faces of the mirror. Okay, and in between, what you have is not a string. This is not a string. This is the amplitude of the electromagnetic wave. Okay, suppose you have a certain wavelength of electromagnetic light between these two mirrors. Since mirrors are reflecting light, if somehow there is a kind of light, portion of light that entered somehow between these mirrors, this light will reflect back and forth, right? And this is nothing but your electromagnetic wave. If this is having a single wavelength, what you see is the largest wavelength that can fit between these two mirrors is going to be in this shape, okay? And This down shape is nothing but you don't have two shape over here. It is the shape of the amplitude between these two mirrors, and it is going down and up and down, up and down. You know, the amplitude of the, what we describe as the amplitude of the electromagnetic wave is principally its electric field amplitude. If you draw, let me draw this zero line over here. Okay, this is the line that you have zero electric field. When the amplitude goes down to zero, you have zero electric field, but it goes down in the negative axis. So it gets a negative amplitude. It goes back again and a positive amplitude. So electric field amplitude will go up and down from positive to negative, okay, indefinitely. But the wavelength where this line is approaching one of the mirrors, you have this electric field is approaching zero. Right at the point of the mirror, the electric field is always zero. It never gets a non-zero value. But if you come towards the midpoint, this electric field amplitude will get maximum at this point, and it will get after the midpoint. If you approach to the other side, the amplitude will get zero again. So if you imagine this as a movie, this line will just oscillate just like a string, guitar string, okay? Just like a guitar string, this wave will oscillate back and forth, okay? And the other thing is that this is the largest wave that you can put between these two mirrors, okay? In fact, what you see over here, if you continue this, like this on the other side, the wavelength is going to be just twice of the distance between these two mirrors. So the largest wave that you can put between these two mirrors, which are a distance of L apart from each other, the wavelength that you can put between these two mirrors in order to get a resonator, a well-defined resonator, the largest wavelength that you can put between these two mirrors, which are a distance of L apart, it is going to be 2L, okay? So, if you have a laser, and if you want to produce a laser, if you want to produce a laser by using these two mirrors, this is the largest wavelength that you can produce by using these two mirrors, which are a distance of L apart from each other, okay? So we start with this, and we will of course continue. This is not the only wavelength, which is 2L, that you can produce a laser wavelength by using these two mirrors. There is going to be more and more different wavelengths that you can put over here. If of course, since we are talking about the wavelength, but also there is a corresponding frequency. A frequency is going to be just C divided by 2L. Okay, this is the let's say if this is the largest wavelength, this is going to be smallest frequency. Okay, so obviously you will have larger frequencies, and I will discuss this. So I will stop over here. Okay, arkadaşlar burada kesiyorum.